João Pereira from the third floor here at IMPA. He'll be giving a talk about tensor decompositions.
Thank you for inviting me to organize the workshop. And so I would say from the organizers, I'm the one that is most far away from networks. And so actually my advisor, he was very close to the topic, and then I kind of drifted away and went for tensors. I work on other things, but I'm really passionate about this tensor stuff. Roberto really didn't want me to talk about tensors, but oh well. And so I kind of got away with doing that. And so the trick is like, you look at the title of the workshop, right? And now you use permutations, which a lot of people have been using here. And so you take some W and K out, you swap the S, and you get tensor, right? And so that's the way I got to talk about tensors. Okay, but to be honest, I tried to make it so I'm going to talk about tensors, but I tried to make something that you'd enjoy in some sense. And so there's this problem that we have on this algorithm that we proposed, which is called SPM. And it's about this model that, so we believe something happens when you have a random model. So something that we've seen it happen is if the tensor components, which I'm going to explain what they are random, then with high probability, there's no bad local maxima. And so we observed this empirically, and we want to show that. And we have a paper where we make headway on that. And so in the end, I'm going to kind of pose an open problem. So Roberto stops looking at me, staring daggers to propose open problems. So I'm going to do that in the kind of the end of the talk in this context. So first I'm going to start talking about tensors. And so here tensors are going to be just multidimensional arrays. So think of a matrix, but now you have, instead of 2 dimensions, like a matrix is like a table of numbers, you have like a cube of numbers, right? And so I'm going to call the order of the tensor, so it's basically the number of dimensions. So a matrix is a tensor of order 2. And by the way, a vector is a tensor of order 1, and a scalar is just a tensor of order 0, right? And now if you do D bigger than 2 is the interesting case for me. Of course, we also work a lot with matrices anyway. So actually for this talk, I don't have to worry much about different dimensions. All of them are going to be the same. So I'm thinking about cubic tensors, what are called cubic tensors. All the dimensions, all the D dimensions of the tensor are equal to n. And so why am I going to focus on this kind of tensor? So, and for a tensor like this, the number of unique entries of this D-weight tensor is n to the d, right? And now tensors have this problem. Not only tensors have a curse of dimensionality because they are huge, they also have a curse of notation. So I'll have to use more indexes. So for most of the talk, I'm going to focus actually on tensors of order 4. So there's going to be 4 indices. Here there's 3 indexes. But so that's a problem we have, but this is how you say the index of the talk. And so I'm going to focus only on symmetric tensors. And so what are symmetric tensors? So a symmetric matrix is a matrix that is equal to its transpose, right? So if you take a matrix and you take its transpose, it's equal. Here a tensor is going to be symmetric if all the D factorial permutations are equal. So transposing any D indices gets you the same tensor. Right? So you might be thinking, okay, that's only a very small fraction of all the tensors, right? So if you take all the tensors that are not symmetric, you get roughly only 1 over D factorial of all these cubic tensors, and even cubic tensors are just only a fraction of this thing. So why do symmetric tensors matter? And so there's three applications or three things where symmetric tensors appear most in applications. And so one of them is thinking about higher order moments. So you take your first moment of your multivariate random variable, that's going to be a vector. You take your second moment, and that's going to be basically the covariance plus something that depends on the first moment, plus its transpose. And so now you have the second moment is just made of two products of the random variables. You can take 3 products. And now that gives you a tensor of order 3, and then you keep going. All these higher order moments are actually symmetric, because if you take xi xj is equal to xj xi xj xk is the same thing. So this is a symmetric tensor, and it's one that arises the most. You can also think of these symmetric tensors as derivatives, higher order derivatives of functions. So the Hessian is a symmetric matrix, and if you take another derivative, you're going to have a symmetric tensor of order 3. So think of these tensors as generalizations of higher order Hessians, right? And then we also have a third thing that, so I could go this way, but unfortunately I don't have any work on this direction. So there's hypergraphs too, and so hypergraphs can be thought of as symmetric tensors. So here, a graph can be thought as of an adjacency matrix, and if the graph is not directed, then the adjacency matrix is symmetric. Now you can think of hypergraphs that are not directed, and now adjacency tensor is going to be a symmetric tensor. And so this is a way where these things arise, and because of all these applications, tensors, okay, so before I go to the applications, there's what we want to do with tensors. We normally want to get information from them. And so to get this information, there's a bunch of decompositions we can consider. I'm going to talk about the most common, the most talked about, which is called the CP decomposition. So what is this decomposition? Is taking a tensor and try to write it as a linear combination of rank 1 tensors. So what is a rank 1 tensor? In the symmetric case, it's just taking a vector, taking a vector and taking its tensor power to the d. So what is a tensor power? So for a matrix, it would be like AI transpose. Now, if you're thinking a tensor of order 3, it's going to be AI, and then AI on another direction. That's like AI cubed. And now you're trying to write this a linear combination of these terms, right? So that's the most common. So the lambda i's are scalar. You can always put the scaling in the lambda i's to assume the AI's have norm 1. And when d is odd, you can get rid of the lambda i's and just have the AI's, because you can put all the scaling in the AI's. Okay, so a nice thing is that when you try to get this decomposition and you apply this in the other cases when symmetric tensors arise as moments, so you try to decompose these moments or try to decompose these derivatives, or even the hypergraphs, you can get a lot of nice methods in applications in a variety of problems, going from mixture models, generalized linear models, hidden Markov models. Also do some learning with derivatives in neural networks and work on independent component analysis. Actually, a lot of the work that has been developed for tensors has been done in the spirit because of independent component analysis, to get something out of a method to solve independent component analysis. And so, okay, this has been some introduction about the motivation about the tensors, but what are these properties of this decomposition? So, okay, this is an example of how these tensors, how decomposing tensors can get you the parameters. So, yes? It's actually, there was 2 algorithms to compute tensor decompositions. One was called CanDecomp, and the other one was Parafac, which, by the way, were already acronyms, and so they joined these 2 in CP. And so CP is an acronym of 2 acronyms. So a crazy thing, yeah. And so here it's an example of how to use this tensor decomposition to get parameters. So if you get the moments, if you calculate the IRR moments of a Gaussian mixture model, you can get that like the centers are going to be given by the moments, and then there's some bias terms that you can take out. And so you can kind of estimate the centers just from the moments. And so if you decompose this tensor here, you get the centers, right? Okay, what are the properties of this decomposition? So there's a theorem, a very big important theorem in algebraic geometry that says that the rank of these tensors is order of n to the power of d minus 1. And so the rank of this tensor is really big. So if you have a tensor of n cubed, right, n times n times n, the tensor can be up to order n squared, right? So it's much more than a matrix. Normally, the matrix n squared entries, you get n. Now n cubed enters, and you get n squared, right? So the rank can be much bigger, and there's this uniqueness. The uniqueness is different than for matrices. So for matrices, this kind of decompositions could be, for instance, eigenvector decomposition, right? So in the eigenvector decomposition, you ask for the vectors to be orthogonal, right? The eigenvectors are always orthogonal. You can also think of it as a Cholesky decomposition, but the Cholesky decomposition is not unique. It's only unique up to an orthogonal transformation. For the tensor decomposition, the transformation is not an orthogonal matrix. It's actually only a permutation. So you can only permute the terms of the sum. You can multiply them by scalars, and that's the only permutation. So this is useful, for instance, in the problem before of the Gaussian mixture model. So in the second moment would give you, like, if you take out the noise of the covariance of the noise, it would give you lambda I AI squared. Let's say you have two terms, lambda 1 A1 squared plus lambda 2 A2 squared. So if you only have this thing, there's no way you can get A1 and A2. You only get the subspace spanned by them from the second moment. But if you add the third moment, then you can decompose it already. So that's the idea, is that because the Cholesky decomposition only gives you your information up to orthogonal transformation, you can't get all the information you get from the second moment, but you can do it with the composition of the tensors of IRR moments. And that's some usefulness of the tensor decomposition. It does have bad news. And so the bad news is that computing this CP decomposition is NPR. So the idea is that, okay, it's NPR, but if the tensors are low rank, then there are provably efficient algorithms. One of them is simultaneous degeneralization if the rank is less or equal than n for tensors of order 3. And then there's this Fooby algorithm for tensors of order 4. There's this Nice method, and there's also most of the algorithms are based on empirical things that work in practice and don't have a lot of guarantees, including these methods for numerical optimization and the tensor power method. And so there's also a conjectured statistical to computational gap. And so the idea here is that the biggest rank a tensor typically has, it's going to be up to n to the power of d minus 1. However, you can decompose, we believe you can only decompose efficiently tensors if the rank is less than n to the power of d over 2. And so what I'm going to talk about, and this algorithm that I'm going to talk about, is an algorithm that can go up to n over to the power of the floor of d over 2. So for even tensors, this gets to the conjectured point, right? And for odd tensors, it's a half term away. And so I I'm going to talk about something very specific of this, something about this algorithm, so I do have to explain the algorithm. So bear with me. So I'm going to talk only, the algorithm works for all orders. I'm going to focus on d equals 4. It's where the interesting thing appears. And so you can take this tensor, which is n by n by n by n, and you can make it flatten it into a matrix. So what does this mean? You take two of the dimensions, n times n, and you make it into a big dimension, n squared dimension. And take the other two and you make it also into n squared dimension. Now you add a tensor, now you have a matrix of size n squared by n squared. Now if you do this, and this is actually a linear operation, I think it makes sense that this is a linear operation. So if you do this in tensors of rank 1, it's actually equivalent to just taking ai squared, flattening that vector, and multiplying it by ai squared transpose. And so what I said is just this, right? Vec ai squared transpose. And so now vec ai squared is just ai times ai transpose, right? So think of it as you take a ai transpose, which is a symmetric matrix, and you flatten it into a vector. And so you can write this sum, organize this in a matrix form, and write this where the vec ai's are in the columns, and then you have a diagonal matrix which is with the lambdas, and then the vec ai's appear again, but on the rows and transposed on the other side. So these are exactly, the sum and this thing is exactly the same thing, but now with the matrix form we can see something interesting. So the first thing is that shows up is that, so let's suppose that the AIs, these vectors are linearly independent. If they are linearly independent, then these vectors are also linearly independent because they're the same matrix, it's just transposed. And this matrix is as rank r, so this is going to have rank r, right? So just by looking at the matrix, we see that the rank of the matrix is the same rank as the tensor. Okay. And the second thing is that, so it's not quite right that this, for instance, eigenvector decomposition would get you these things because the AIs might not be orthogonal. But one thing you get is that if you do, for instance, a orthogonal eigenvector decomposition of mat T, you're going to have a span for the columns of mat T, and these columns are actually the span of this thing. So basically, if you take this span, which is going to be a subspace of dimension n squared, and you make it into subspace of symmetric matrices, now you have a subspace of symmetric matrices that's spanned by the AI's AI transpose. Right? And so you have a way to project into this space. You can describe this space, right? But you don't know the AIs. And so you do get an orthonormal basis for the AI for this space, but you don't know the AIs. You just can get this from the eigenvector decomposition of the matrix. So now the question is, suppose you have a subspace of symmetric matrices. Can you find the rank 1 elements in this space? Right? And so how to find rank 1 matrices in a subspace of symmetric matrices? So it turns out this problem, for any A, it's NP-hard. And so you can, you can encode any polynomial system you want into this problem. So if you have any multivariate polynomial system, you can write a version of it that you can write an A for which the rank 1 elements in this A are the exact solutions for the original polynomial system, right? And so it's really NP-hard. What can we do? So we're going to try to maximize this function. So this function takes a vector, calculates the vector times its transpose. This is now a matrix. Project into A, and then you take its norm, right? And so the vector x has norm 1, 2. So this is non-convex. So these are some nice properties. So one is that f is non-negative, right? Because it's a square of some real number. And then it's also less or equal than 1, because it's less or equal than the norm of XX transpose. That's going to actually be the norm of x to the 4. And so norm of x to the 4 is equal to 1. Okay, so f is between 0 and 1. And what happens when f is 1? If f is 1, that means that, so the norm of XX transpose squared is equal to the norm of the projection into A plus the projection into A perp. Right? If f of x is 1, means that the projection of XX transpose to A perp is 0. So it means that A XX transpose is orthogonal to A perp, so it must be in A. So this means that we have a rank 1 element in A. So if we find a global maxima, here the global maximas all have function value 1, we get what we're looking for, rank 1 elements in the subspace. Okay, there's still something, right? So we were thinking about finding rank 1 elements in A, right? But there are more rank 1 elements than the ones we're looking for. So this is an answer that you can answer. This is something you can answer with the algebraic geometry. And the point is that if the AIs are generic, so here generic means that there's a polynomial on these AIs that must be different than 0. So in other words, for instance, if you sample these AIs at random from a Gaussian distribution, from the uniform distribution on the sphere, the probability of this happening is 1. So the measure set where this doesn't happen is measure 0. And so if the rank is less than the n choose 2, then the AIs are going to be, the only rank ones are going to be precisely the ones we're looking for, which are the AI transpose. And so this is nice. This is the ones we're looking for. So these tensor components are global maxima of the objective. And so we want to maximize this. The ones we're looking for are global maxima. How do we maximize this? We use the power method. And so the power method here is just going to be you project XX transpose into a matrix, into A, and that gives you a matrix. You apply xk to that matrix, and then you have to add something here, otherwise this might not converge, but half is enough. We proved that in our paper. And then this is going to converge to a second order constrained local maxima. Here constrained means that we're just optimizing in the sphere, right? And so it's going to converge to a second order local maxima if you think about manifold optimization. Okay, so this is a way to do the algorithm, right? Now I'm going to go back to this power method, right? This is going to be most of the talk afterwards. But before I keep going on it, it's important to think, okay, so you get a tensor component. Let's say you got AI. What do you do with it, right? And so there's this deflation procedure you have. And so suppose you got AI. And so for ease of notation, I'm just going to suppose that the one I got was the first one, right? And I just can do this by relabeling, right? And so if I got the DA1, I can think about this matrix. It just takes mat T, and then subtracts a constant times this VKI squared transpose, right? So if you do this, it's easy to see that you get, because of the formula for mat T, you get this thing here. And so this thing here is going to, we saw that the rank of the tensor is equal to the rank of the matrix. In particular, this thing is going to have rank R, except if tau is equal to lambda 1, where it's rank R minus 1. So we can think about it this way. So suppose you have a full rank matrix. Well, actually, it's not a full rank matrix, but so suppose you have some matrix and you subtract some vector, some rank 1, do some rank 1 perturbation into it. When does it drop rank? And this is actually something that's easy to calculate, and the formula is here. And so it drops rank if this tau here is equal to 1 over this thing here. And so once you get the 1, you get the lambda 1, and now you can take it out and then keep going. And so you never get the same A1 twice, right? So in practice, we don't really do this and then get another eigenvector decomposition. We update the eigenvector decomposition directly. Okay, and so the algorithm starts by doing getting the eigenvector decomposition of mat T. Then from that, you get like a way to project into A. You do this power method, you deflate, and then you do these R times, and then you're good to go. And so why did I spend, why I'm talking so much about this algorithm? It's because this algorithm is really fast. And so how fast am I talking about? So this beats everything by like 10 times or something. So the red one is what's called, it's a provable efficient algorithm. So the dependence is polynomial on the time, but the order of the polynomial is really big, and so it takes a long time. Now, there's algorithms that we don't really have guarantees. These are like algorithms that rely on optimization to solve the problem. And they are fast, but ours is like 10 times faster on average, like order of magnitude faster. So notice this is log scale, right? So we're talking about 10 times faster, right? And so not only this algorithm has a lot of nice mathematical properties, it's much faster than what's going on. And that's why we really want to understand this further, right? And so the algorithm is, so the deflation part is just linear algebra. And the first part where you just get the column space, that's also only linear algebra, right? And these two parts are really well understood. The only part that is not really provably efficient is the optimization part. I wanted to understand it better. So the first thing we did was numerical experiments, right? What's going on? And so what we did was the following. So we got, so we fixed n, and we got, we generated a lot of AIs with the rank varying, right? And so we repeat this power method experiment, and we record how many times it converges. So we record how many times it converges to a global maxima, when it converges to something that was not a global maxima, but it's a local maxima, or if it did not converge at all. So what we see is that, so notice here the rank. So the maximum rank you can do for n equals 20 and d equals 2, which in this case is 190. That's the cutoff rank we get from one of the propositions. And for that rank, so after that rank, you start getting more rank ones than ones you had there to start with. That's the threshold, right? And so we see that up to 170, practically like 90, I think it's 97% of the times it converges to a tensor component. Right? And so we're seeing that if your rank is a little bit below the threshold, you're getting most tensor components at the first time, most of the time, right? And so, and then it drops really fast. And then here, there's an interesting thing where, so more rank ones appear if above the threshold, then you see that, right? So the red one is like, there's more rank ones after this rank threshold, and you really see that. So that confirms with what we think it would happen. And so we see this in practice, and we wanted to get some results on this. And so we looked at what people have done in this area, and there's this paper that studies only the power method. And so what they talk about in terms of the power method, so think now of a tensor without the lambda i's, it's just ai to the fourth, right? And think of these AIs as being Gaussians. And so instead of maximizing the functional we gave you, just take this tensor and you basically contract it with x 3 times, and then you get a vector, and then you keep doing this, right? And so this thing, it's equivalent to maximizing this function here on the sphere. And so you can do this, and then the question is, what this give you? And so the point is that if the AIs are Gaussian, you don't expect there to be a lot of correlation between the AIs, and so these will tend to approximate one of the AIs. And so that's what they proved. They proved that if the rank is less than n squared, then with high probability, there's exactly 2R local maxima in a level set above 3R. And so all these 2R local maxima are close to one of the AIs in some norm, but depends on n and R. And so this is the result. And so I want to say that for this problem, the expectation of G is 3R. Actually, I got it wrong. It's not 3n, it's 3R. And it's easy to calculate the expectation, right? Just the expectation of this random variable here. These are all Gaussian, so this is easy to calculate. And so the one they show is just a little bit above. It's still not enough for them to show that just sampling a random point. So this term here is enough to tell you that just sampling a random point is not enough to get you above this level set, to be sure that you're above this level set where you're not going to find bad local maxima. And so it's still not a provable algorithm in some sense. It's also a bad algorithm in practice, and I'm going to show you why. So these errors here are kind of big in practice. It makes sense, right? It's just going to be, so suppose R is close to n squared, then it's just going to be 1 over n, right? If n is 100, you get like square root of 0.1, you get only 0.1 error, right? So that's what you see, right? The error is really small, is really big. It's better than random. So random gets you to 10 to this order here, you get a little bit below that. And so at the same point, I want to compare with the algorithm, the objective I gave before, where if you're doing this thing where you project, you get this A that I told you about in the SPM objective, you're actually getting the right AIs because you do get the correct solution up to numerical precision, right? And so we want to analyze this SPM objective, right? And so just to show you, so this PM objective, if for different angles, for instance, this is thinking about the dimension 2, right? And two elements in R2. And so you can think of these two vectors just thinking about their correlation or their angle. So if you think about this angle, if the angle is 90 degrees, then both objectives coincide in some sense, and the maximums are going to be the same. But then the red points are the actual maximum. And you see here that in blue, for instance, if the points are very correlated, PM stops seeing 2 maximum, just sees 1, while SPM is still seeing 2 maximum. And here it gets the maximum correct. Here there's some error. Here he gets it completely wrong, right? So there's these two objectives. And so the power method is this objective here. The SPM objective, so I told you that in the algorithm you can get this way to project from the eigenvector decomposition. But you can also, if you know the AIs, for theoretical analysis, you can assume you know the AIs, right? If you know the AIs, you can get the formula for the objective depending on the AIs using normal equations. And that formula is going to give you this formula here. So you have this G, which is a Gramian matrix of the inner products between the AIs, which are the tensor components. You invert this matrix, and then you have this phi I, which is the inner product of AIs with X. And you take that as a square in all things, and the G square, and then you invert it, and that gets you F. And this F here is going to have the AIs to be exact local maxima, right? And so there's these two objectives, and in our paper in 2021, we got some results that are similar. One is for systems that are almost orthogonal. So if the AIs are close to being orthogonal, and what does close to being orthogonal means? So if a matrix is orthogonal, this here is going to be 0. this is always bigger or equal than 0. It's 0 if it's orthogonal, and so if the AIs are almost orthogonal, then there's no bad local maxima. The only maxima are the global maxima that we're looking for, the AIs plus or minus AIs. So another case, and this is the case I'm going to focus the most, but I think because I think it's the most interesting to you, is when you sample the AIs at random. So if you sample the AIs at random on the sphere, you can get all the way up to order of n squared. You see that either the local maximums, their function value is really small, or it's the ones that we're looking for, the AIs that we're looking for. And so the proof, and how we prove this, is the part of probability is actually just using some assumptions that hold that probability and using them then after the proof. So it doesn't have, so the probability of this, the part of the proof is basically here. And so there's these three assumptions that we use. One of them is that A, so A you can think of it as sampled as a matrix with columns sampled from the uniform distribution over the sphere. It has a RIP property. And so that holds with high probability, and that's well known. Second thing is that the inner products between the AIs and AI and the J are bounded by log R divided by n times a constant. So C1 and delta and C delta are all constants, so you can choose whatever you like. And then the third one was a little bit harder to prove, was that the second the norm, so the smallest single eigenvalue of the Gramian is bounded from below, or the operator norm of the inverse. And so, but all these three hold with high probability, and so we conditioning on this event happening, and then we show that the result we showed before holds. So the proof is actually goes a little bit like this. So think of the red as the thing the level set which we were not able to show there's no bad local maxima. And then after that, here on the blue, we show that there are no bad local maxima. And then on the white, we show that the function is concave. And so what that does imply, if it's concave, it means that there's only one at most one global maxima there. And we know there's a global maxima in there because it's one of the AIs. And so that's the sketch of the proof. And so the first step is using some inequalities to show that the maximum correlation between the AIs and the X star has to be above some function like this. And so the point here is seeing that if F is bigger, then this thing is going to 0, and so you have something that is really big. And so it tells you that X must be close to one of the AIs. And now that X must be close to one of the AIs, you show that when X is close to one of the AIs, the function is concave. And this concave means we're thinking about optimization on a manifold, on the sphere manifold. So concave in that sense. And then the AIs are global maximum there. The thing is concave, so they must be the only global maximum in those caps. Here, what I did not talk about is first that what I did for d equals 2, actually for order 2, it actually also tensors are of order 4 actually holds for all tensors. So our analysis is for all tensor orders, not only for d equals 2. Just easier to explain. And we also do something which we call a robust analysis. So the robust to noise. So in practice, you never see a truly tensor without noise, right? So you have some noise, and so you have this norm. So think of it as you have this orthonormal basis for this space tilde A, where tilde A is not the true A, but is close in norm, and so this is norm we use, the norm of the projection NA and minus PA, this is operator norm. This norm is bounded by some delta A. And now you have this term delta A, and then you get all these kinds of bounds with this delta A, including, for instance, if you have this delta A, the level sets now become a little bit higher, depending on delta A. And then also, the global maxima now are not going to be AI, because the function is not really perturbed. The global maxima are not AI, but they're going to be close. And how close how close they are by this delta A. And it's a bound that when delta A is 0, then they coincide. This makes sense. And there's also this end-to-end analysis of the algorithm, of this SPM algorithm. By the way, I haven't told what SPM stands for. It's called subspace power method, because it's like a power method on this subspace, right? And so that's why it's called subspace power method, or SPM for short. And so what is this end-to-end analysis of SPM? You take, so what you can do, you can get eigenvector decomposition. So suppose you have a noisy tensor, T, right? So if you have this noisy tensor in some norm, which some norm I'm going to define on the next slide, that implies that the approximate, this tilde A is also close to the original tilde A. So you do eigenvector decomposition, and then you get a tensor component, and now you have error bounds of the tensor component coming from the robust analysis. And then these error bounds propagate in doing deflation, and so you do these error times, and you have like this very long analysis, and you get an analysis for the whole error of the algorithm. And so this is what the analysis looks like. This is a very big theorem. Let's just put here the important. It's very hard to parse, but so the noise here that we consider is thinking about the matrix version of the tensor, and then the operator norm of the difference of the matrix versions, the matricized versions of the tensor. So you take the tensor, you make it matricized. You take the original one, you do it the same thing. You take the difference, and you take the operator norm of that. And that's our error, and with that error, all the things follow, and so you can bound things like the tensor components, the error, the error on the tensor components, and here on the eigenvalues on the lambdas, which are the tensor coefficients. And so in the noiseless case, where delta M is equal to 0, algorithm 1 returns the exact decomposition of T. If the original T is noiseless, then SPM works, right? And so now to discuss some open problems, a little bit anticipating the staring of Roberto, I do have some open problems on this thing. And so one of them, it regards the definite case, so nothing random. And it's just simple things. So if the rank is equal to n, so this is a tensor that is the rank is very, very low. And so this is the case also, the rank is being as small as you want it to be, because if the rank is less than n, you can always project to the subspace spanned by the AIs to have the rank to be equal to n. So this is the smallest rank in some case that you can consider. So if R is equal to n, I believe that there's no bad local maxima. You can't ever do it. This is a conjecture I have, and we've only been able to prove it for R equals 2, R equals n equals 2. And then the other case, and maybe this is the most interesting for you, is if the AIs are sampled uniformly on the sphere, I do believe that there's no bad local maxima. So that red region that I put there before, I do believe we just were not able to get there. And so I do have some ideas to get there. So the original paper, they use something which is called the Kac-Rice theorem. And so the idea, the Kac-Rice is a formula to calculate the expected value of zeros. So most of the times it's used for univariate functions, but they do use a multivariate version. And so the idea is that the expected version, the number of expected, the number of expected bad local maxima or second order local maxima in this set is given by this formula here. So it does involve a lot of things, like you have to think about what is this peak rad of f is the distribution of the gradient of f. And so the gradient for the SPM function is a little bit more complicated than the other case. In the other case, it's just AIX to the power of 5 to the power of 3 times AI, and you can kind of bound things, but these things sum over all r's, but it's more easier. For our case, there's a Gramian inverse there that complicates things. In particular, we don't even know how to calculate the expected value of f of x. This is a very simple thing. In the other case, just 3r. But in the other case, so f of x is just AI transpose x to the power of some n, right? This is a vector, Gramian inverse, and then that thing transpose, right? So the part of the Gramian inverse, having an expectation of a Gramian inverse that involves Gaussian elements, you can do it with Gaussian on or uniform over the sphere. It gets you the same thing. We don't know how to calculate that. So if that's such a simple thing, if you want to try to calculate, you're welcome to try that. And these are the open problems. I thought I would talk about some, and I'm happy to take questions or more open problems or things we might have not yet considered. And so this is the summary. I talked about this, what is the symmetric CP decomposition and some algorithms for this. And then we presented this SPM algorithm that's really fast and has some nice guarantees. And then I talked a bunch of time about this optimization landscape. And that's it. So these are the two papers. So the paper on the optimization landscape has been in Europe, and we recently resubmitted the first paper, which we postponed for a long time to resubmit. But we finally did it. And yeah, the code is also online.